In mathematics, in the field of differential equations, a boundary value problem is a differential equation together with a set of additional constraints, called the boundary conditions. A solution to a boundary value problem is a solution to the differential equation which also satisfies the boundary conditions. Boundary value problems arise in several branches of physics, as any physical differential equation will have them. Problems involving the wave equation, such as the determination of normal modes, are often stated as boundary value problems. A large class of important boundary value problems are the Sturm-Liouville problems. The analysis of these problems involves the eigenfunctions of a differential operator. To be useful in applications, a boundary value problem should be well posed. This means that given the input to the problem there exists a unique solution, which depends continuously on the input. Much theoretical work in the field of partial differential equations is devoted to proving that boundary value problems arising from scientific and engineering applications are in fact well posed. Among the earliest boundary value problems to be studied is the Dirichlet problem of finding the harmonic functions. The solution was given by the Dirichlet's principal. Explanation: boundary value problems are similar to initial value problems. A boundary value problem has conditions specified at the extremes of the independent variable in the equation, whereas an initial value problem has all of the conditions specified at the same value of the independent variable. For example, if the independent variable is time over the domain 0, 1, a boundary value problem would specify values for it both and, whereas an initial value problem would specify a value of an at time. Finding the temperature at all points of an iron bar with one end kept at absolute zero and the other end at the freezing point of water would be a boundary value problem. If the problem is dependent on both space and time, one could specify the value of the problem at a given point for all time the data, or at a given time for all space. Concretely, an example of a boundary value is the problem to be solved for the unknown function with the boundary conditions without the boundary conditions. The general solution to this equation is from the boundary condition one obtains, which implies that from the boundary condition one finds, and so one sees that imposing boundary conditions allowed one to determine a unique solution, which in this case is types of boundary value problems. Boundary value conditions: a boundary condition which specifies the value of the function itself is a Dirichlet boundary condition, or first-type boundary condition. For example, if one end of an iron rod is held at absolute zero, then the value of the problem would be known at that point in space. A boundary condition which specifies the value of the normal derivative of the function is a Neumann boundary condition, or second-type boundary condition. For example, if there is a heater at one end of an iron rod, then energy would be added at a constant rate but the actual temperature would not be known. If the boundary has the form of a curve or surface that gives a value to the normal derivative and the variable itself, then it is a Cauchy boundary condition. Examples: summary of boundary conditions for the unknown function, constants and specified by the boundary conditions, and a known scalar function specified by the boundary conditions. Differential operators aside from the boundary condition. Boundary value problems are also classified according to the type of differential operator involved. For an elliptic operator, one discusses elliptic boundary value problems. For an hyperbolic operator, one discusses hyperbolic boundary value problems. These categories are further subdivided into linear and various nonlinear types. Applications: electromagnetic potential in electrostatics. A common problem is to find a function which describes the electric potential of a given region. If the region does not contain charge, the potential must be a solution to Laplace's equation. The boundary conditions in this case are the interface conditions for electromagnetic fields. If there is no current density in the region, it is also possible to define a magnetic scalar potential using a similar procedure.